Hello, my name is Colby Mazzuca. I am the CFD engineer for Richard Childress Racing.
And I'm Arnaud Froidmont. I'm a HPC solutions architect at Oracle.
And today we will be presenting how RCR is winning the race with the Oracle Cloud infrastructure. Like we said, my name is Colby Mazzuca, and I'm here with Arnaud Froidmont. So a brief background, what is NASCAR? NASCAR is the acronym for the National Association for Stock Car Auto Racing. It is an American motorsports event best known for its stock car racing. Some of the quick facts: we race with up to 40 cars at one time on track. We're best known for racing on our oval racetracks, ranging from the short tracks of Bristol at just over a half mile long to the super speedways like Talladega and Daytona at over 2.5 miles long, where we will frequently reach over 200 miles per hour top speed. A brief overview about Richard Childress Racing. RCR was founded in 1969 by Richard Childress. It is one of the most longest running and most storied organizations in NASCAR today. We have accumulated over 16 championships and 240 victories across the NASCAR Top 3 series. We currently field 2 teams in the NASCAR Cup Series and 2 teams in the NASCAR Xfinity Series. There you can see the 8 car of Tyler Reddick and the 3 car of Austin Dillon, our 2 Cup car drivers this year. So RCR, we use the Oracle Cloud to provide our HPC resources for our CFD program within the Aerodynamics department. A brief introduction to aerodynamics and CFD. Computational fluid dynamics, otherwise known as CFD, is a way that we can numerically simulate fluid flows using high-performance computing and softwares. Our primary use case for CFD is in the external aerodynamics of our race cars. Their picture on the left, you can see the 3 areas of interest in external aerodynamics. We are mainly focused on drag, which is the force opposing our forward progress. We aim to reduce that force. Lift, which is the force that wants to bring the car off the ground. We generate negative lift, otherwise known as downforce, to push our car into the ground and help it corner better. And then since we are primarily focused on our oval track programs where we consistently turn left with no right turns, we actually focus on a third force called side force. Side force is defined as the force that wants to push our car up to the right. And we aim to generate a negative side force and help turn our car aerodynamically to reduce some of the mechanical strains on the force required to turn a car at around 200 miles per hour. And the benefits of CFD, this allows us to simulate all of our parts and designs and their aerodynamic impact without having to make physical parts and take them to the wind tunnel and the time and costs associated with physical prototyping. So how do we use CFD? We kind of break it down into 3 main stages. First, we design our parts. You can see there the tail of the car and our new part in red that's got some deformities in it. Second, we take it onto the solver, which is where we rely heavily on the Oracle Cloud infrastructure. And in the final phase is the analysis phase, where we then need to dig deep into what that simulation actually provided to help understand the aerodynamic impacts that those designs had. So the first process in the design phase is working in CAD. We maintain a complete CAD model of our race car. The CAD model serves as the foundation for any designs or parts that we want to put into CFD. The CAD model is actually an exact digital twin of the race car that's on track. It is fully detailed, and just about every part you see in the physical race car, we have modeled in our CAD model. If we look at an example case here of how we can use CFD, in the design phase, we want to design as many iterations that we want to simulate in CFD as possible. So that image set on the left there is our front anti-roll bar arm. It's the kind of stock mechanical suspension only part. And we are interested in getting an aerodynamic advantage out of that part. So again, the first part in the first phase of design, we want to draw and create as many possibilities as we can. So going from left to right there, now you can see we've got a sort of a C channel part on the bottom, a little bit of an H channel. We've got that one that slopes out from the inboard to outboard, and then we've got a really crazy one that has a big swept edge that dangles out into the airflow. And again, our goal here is to try and gain an aerodynamic advantage from an otherwise non-aerodynamic part. Moving on from the design phase, we have now our parts designed in CAD. We now need to solve that CFD case, and this is where we rely on the Oracle Cloud infrastructure the most. We put our designs into the CFD software, and our typical CFD case is over 350 million cells and almost 55 gigabytes of data per case. We run up to 150 runs per month, which quickly adds up to over 8 terabytes of data every month. And that's why we rely on Oracle so heavily to provide those HPC resources. Typical cases run on anywhere from 300 to 700 cores per case. The second stage, or the final stage in our CFD process, is the analysis stage, where we then need to interpret the data and make decisions regarding the aerodynamic performance of our design. The initial step in the analysis phase is our automated post-processing routine, which generates over 700 standardized images per case. So again, for those 150 cases per month that we run, we output 700 images per case. We have utilized the Oracle Cloud to automatically kick off our image generation routine on a GPU-based cluster after a CFD case has completed. So purely automatic. They kick off after one another and switch to a different type of cluster. Beyond just the standard image set, sometimes we will need custom imaging to get a further, deeper understanding of what's going on. Our goal in this analysis phase is to understand the flow mechanisms that the new parts have created. So understanding why those front anti-roll bar arms had the aerodynamic effect that they did, be it positive or negative, we want to understand what happened there to then better inform our designs moving forward. If it was a positive change, we can maybe investigate where that positive change came from and try to exploit it a little further. If it was a negative change, we also want to learn that, so that we can alter the design away from that and maybe go in an opposite direction to try and yield an aerodynamic benefit. With this example here, we've kind of got some pressure plots, some oil flows on those front anti-roll bar arms. We're looking at some streamlines there and really trying to visualize what is the air doing. And by examining a range of these images, we can then start to paint a clear picture of what that part did and figure out why it's working or not. Beyond CFD, we then take a lot of our parts to the physical wind tunnel. In our example case, out of our 4 original front anti-roll bar arms, if we assume 2 of them showed positive aerodynamic gains, we would then take those 2 to the rapid prototype stage and to the wind tunnel. For the wind tunnel, we do not make a full production level part. We kind of rapid prototype. We utilize a lot of additive manufacturing, such as 3D printing, to get the general picture of what the parts are doing without having to, again, sink more resources into making a full part. If they prove favorable in the wind tunnel, it is likely that it will make it onto the race car for Sunday's race. If not, we go back to the drawing board and go to CFD and repeat the cycle. The benefits here are that out of the 4 example front anti-roll bar arms, only 2 showed positive, and we only had to make 2 to go to the wind tunnel instead of having to make 4 of them and find out 2 were not worthwhile. When RCR first moved to Oracle Cloud, we had our first production level CFD job running in just 2 weeks. And the performance that we saw versus our previous HPC provider, we saw a speed up of over 200% per case. Now I will hand it off to Arnaud to tell you about how that was achieved.
So running CFD on Oracle Cloud is something that is very common, and our team has tons of experience doing it. And so it was very straightforward to help RCR just move on to a platform and start using. The first thing that we do is we have integrated with the scheduler. In this case, Slurm. Basically, each job that will be submitted to the scheduler will have its own infrastructure created just for that. So clusters are created on demand. The advantage of is you always have the right type of node, the right number of nodes, and as soon as you're done, we shut them down so that we don't incur any extra costs. We'll see later that the meshing, the solving, and then the post-processing all happen on different types of cluster. The other thing that we did to avoid to be able to run very quickly is that we did not use a parallel file system. So all of the data actually is stored in what we call object storage. So those are just objects that are stored, and you can go back and forth between the different stage. The other advantage of having all of that living in object storage is that you can have policies. And you can say anything older than 3 months can get deleted, and then they can keep the data for as long as they need, or as they need to by regulation as well. And so each cluster has its own small shared file system, so small NFS to share between the nodes. But other than that, it just lives for the time of the job, and then we don't store anything on a parallel file system, which is making things a lot easier. You don't have to maintain, you have to say I'm going to go and delete those files and so on. And then the other thing is that Oracle engineers really help from A to Z. As much as we can, we help RCR, whether it's from spinning up the cluster, configuring it to spin up different types of nodes, or if an issue occurs, then we can really jump on and really help with it. So that's and then the other aspect is Oracle engineers have lots of experience with CFD and a lot of the other HPC workloads. And so even when we see issues with the workload, we can help, whether it's to tune some MPI flags or any of those things to make it run faster or just avoid any errors. And so, yeah, we help us as well with the infrastructure as with the application. We don't know all of the applications, but a lot of them are very similar, and just knowing what to run, what to add in MPI really goes for a lot of the HPC workloads. And then the last thing is 90% of the deployment is very generic. Anyone that's using a scheduler that needs nodes to be kicked off. So we have what we call a stack that we can use where people can just launch a job, and then the cluster will come up. It's just a matter of installing the right application. So in terms of data flow, we see here we have the CAD design that's being done on Colby's computer or other engineers, where they actually do the CAD locally, and then they kick off the job and submit them onto Oracle Cloud. To go from one to the other, they use the object storage, so it's very easy to upload cases to object storage, whether it's through the console or through some API commands. And then we see that we're going to see a 2-node cluster for the meshing. You see here, then once it has mesh, the mesh is then passed on to the 20-node cluster. And so we are giving all of the data as the output of the meshing is the input of solving. And now we can actually run it. And we said 20 nodes. It kind of depends a bit of the case. Some cases are running on 10 nodes. Some cases are running on 20 nodes, depending on the size of the case and if it's transient or not. So that's depending. Not all of the jobs are going to run on the same size cluster. And then the final step is to provision a GPU node. So all of those pictures, they can really benefit from having a GPU. In our case, it's not the latest and greatest. It's still a P100. They are doing an extremely fine job at generating those pictures and doing it quickly. And so they can run the software to generate the 700 images, and then they are pushed back. Everything is pushed back to object storage to be stored, so that if they need anything from that case and they need to manually go and check things, it will be in object storage. It will be very easy to redeploy on another GPU cluster if they need to do manual work. But other than that, all of the images and logs are just sent to Azure, in this case, to use the Power BI that they have over there. So it's really, it's kind of, again, a multi-cloud approach where they had something that was running well on a different cloud. We don't want to reinvent the wheel, so let's just move those images over there and then use what you have done before. So use Oracle Cloud for what it's good at, and then if you have something working well on another cloud, why not keep it? And so if we now look at the architecture, and so you see a lot of different boxes, it's because everything I've told you, a lot of those stages can happen with multiple cases. So you can mesh 2, 3, 10 cases at the same time, or solve as many as you need. And so what you see are you see some meshing cluster at the top, the 2 nodes cluster, and then you see 2 solving clusters with a lot more machines to actually do the bulk of the work. You also see a GPU node there in the yellow box to do the post-processing. So that's kind of like the meat of what we've been using. How the user accesses it, if you see on the left, you see a bastion with Slurm, and the bastion is basically where you can go and submit your script. So from an engineer standpoint, that's where they go to submit their script. They don't have the need to even log on to any of the meshing nodes or the solving nodes or even the post-processing if everything happens correctly. They just basically log on to the bastion, submit their jobs, and it's done. They can visualize the results in Power BI. So yeah, that's basically the architecture. Very simple. You see the object storage here on the right, where everything is pushed and pulled from when needed. And so the next steps is a lot of the CFD softwares are now trying to move to GPU computing, and it used to be that a lot of them could use a little bit of GPU. They were doing most of the work on CPU and offloading a little bit to the GPU, which very often wasn't very effective. But now there's real work being done to run almost entirely on the GPUs. And there you can utilize things like 8 A100 GPU, which are extremely powerful machines. And between the CPU and the latest GPU node, you can have a 32x turnaround time. So you can go 32 times faster on one GPU versus 36 or versus 128 core CPU machine, for example. And those are preliminary numbers, so we'll have to see that all of the solvers are supported, and then some of those issues that still need to be figured out by the ISVs. But what we do see is that at list price on a cloud, it would mean that the cost would be like 1/8 of the cost from what we have today, running on 800 cores versus running on 816 or 32 GPUs, depending on how well we can parallelize the case. And so we have those machines available at this point. It's just a matter of having the ISV be ready and provide the code to actually run on those GPUs. And so that's probably going to be the next steps to see if we can make this even more efficient. So yeah, we'd like to thank you for jumping on and listening to what we did here. And our RCR was really able to utilize Oracle Cloud to get results faster and cheaper than ever before.
Yes, thank you very much.